everyone. It's my great pleasure to introduce our webinar speaker, Dr. Yun Liu, today. And Dr. Liu is one of the most influential researcher in the intersection of AI for healthcare. He's a senior staff research scientist at the Google Research, and where he leads a lot of groundbreaking work, research applying machine learning and generative AI across medicines, from pathology to ophthalmology to dermatology, radiology, and beyond. And if you want to learn about the AI, how AI can transform healthcare, go to Yun's Google Scholar page and read his papers. And there's a lot of exciting papers there and published at top journals such as Nature, Nature Medicine, JAMA, Nature Biomedical Engineering, MPJ Digital Medicine, Medical Image Analysis, and so on. And some of the work that's already become pretty classic, I would say, like the large language model encode clinical knowledge, deep learning enabled medical computer vision. And in fact, one of the paper I enjoyed most and I often recommend to the students in my class is the work your JAMA paper, how to read an article that use machine learning. And this user guide to medical literature published at JAMA, I think it's quite a few years back. And it's one of the class paper explaining how AI model works in medicine, and it's giving a lot of a practical framework to mostly clinician, but also good for the students in my class. And one other thing I want to say is today Yun's contribution don't stop at research paper. His group has released many exciting models, applications he will talk about today, some open weight models and some imaging foundation model and molecular understanding model. So I'm super excited to have him here. And please join me. Welcome Dr. Yun Liu.
Great, thank you for that introduction, Zima. Yeah, it's a pleasure to be here. I think Zima has been one of the foremost researchers in this space, way back to the Dr. AI kind of like classic paper. Of course, slightly before the Transformers era. But definitely a classic read as well. So today I'll be talking about kind of like our work in this general space. I won't be, I think, going through each paper in as much detail, but I hope to provide a pretty broad coverage of our work in the space, the kinds of stuff we're releasing that hopefully maybe can be useful to people out there, and at the same time just really provide an overarching kind of like lessons learned about what we're learning across these different projects. And of course this is work by many people, not myself definitely, and so I'm representing their work, and it's many hardworking and talented people involved in this. So I have this template slide that's kind of a disclosure. I do work at Google and own Alphabet stock. So in terms of the kinds of stuff that we do, it spans many different domains. And the way we've laid it out on this slide, I think it's more kind of like classically how we were thinking about different modalities and different kinds of application areas per modality. And this is, I think a lot of these are getting kind of like incorporated into kind of like general multimodality work. And this is a trend that's been happening over time, not just in our group, but across many groups as well. So maybe taking a very slight back and thinking about the history of how we as a field got here, the classic machine learning setup really was that, hey, you have data and you figure out ways. So let's say these data are images, and that's a complex kind of like input data. So it's really hard to work with images directly because the pixel values are just, in many cases, RGB values. And you're trying to figure out how to map these RGB values into something useful. Classically, one would do feature extraction, figuring out ways to, to compute the histograms, to do edge detection, and a bunch of other things. And then you figure out ways to use a data-derived way to weigh these different features that you extract to produce some kind of output. Now, as we entered the deep learning era, maybe about 10 years ago, and probably with one of the pioneer works in the space being AlexNet, a lot of the work started to really drop a lot of the explicit feature engineering and rely on implicit feature engineering coming from a deep neural network and using that propagation to learn this. And really what unlocked this kind of work as opposed to feature engineering was the availability of faster computers and accelerators, data sets, and some algorithmic improvements as well, all at the same time. So the convergence of those factors was what really enabled this class of work using deep neural networks. So in our team, the kind of work that we started with when that first happened, this was back in 2016 or so, was this first JAMA paper that we had. And this was about using deep learning to detect diabetic retinopathy, which is a kind of diabetic eye disease, in retinal fundus photographs. These are photographs of the back of the eye. And so these are photos of the retinal fundus. And these are little orange, sort of like circular photos. They can see signs of diabetes in a person with diabetes. And the task here from a machine learning perspective was to categorize the input images, which are, depending on the size, anywhere between 300 pixels all the way to 700 pixels or so, into 5 different categories, depending on which scale of diabetic retinopathy you're using. And in this initial JAMA paper, what we showed was that by brute forcing this, by collecting upwards of 100,000 images and almost a million labels, that we were able to predict DR, this disease here, with very, very high accuracy. And this paper described both the development of that algorithm as well as the validation on an external data set. So this was in JAMA, was one of the early work in that space. A couple more papers, not from our team, I think landed a couple of issues after as well. Now, shortly after, maybe a couple of years after, we improved upon this work, mostly still working in the data space by trying to understand what factors can drive the performance of this algorithm up further. In initial work, the performance that we're observing was that the detection performance was on par with trained graders. So these are individuals who are explicitly trained to do grading for DR, and the performance was on par with them. Here, what we then showed was that there's some amount of data noise in the sense that given the same image, there are people, graders, trained graders, who will provide different labels for the exact same image. And so a lot of the work here was really about understanding that particular problem and getting more labels, getting expert labels, and getting adjudicated labels where graders can discuss any disagreements. And by doing so, we managed to get a much cleaner noiseless data set. And that noiseless data set we used for as a validation set, so for tuning purposes. And we showed that by doing that, we actually got the model performance up to be much better and on par with eye specialists. This particular work was done in collaboration with some of our partners, and over time, the next few years, we did further validation work and development work as well for both DR and several other diseases in the space, and got validation done both in India as well as in Thailand. In particular, we also launched a few prospective studies with our partners in India and Thailand. In Thailand, this was a multi-center study. Now, since then, in the years, we've worked with Verily to launch this deep learning-based algorithm as a medical device, and eventually, and it got CE mark in the EU as well as a regulatory clearance in other jurisdictions as well. And after that, we've gotten more than 500,000 patients benefiting from this DR-based screening in India. And one interesting thing we did is that over that course of work, we also monitored its performance. And so in India, what we then reported was a random sample of a few thousand patients. And we looked at the performance of the DR algorithm and how it worked on real life patients. So no longer in a study setting, but on patients who were actually using this to determine their eye screen. So that was a lot of the work that we were doing specifically in diabetic eye disease. Now, at the same time, there was a class of problems that later on was coined the term oculomics. But another way to think about this is how do you do more with less? And how do you tackle the novel signals kind of like space? One of the early work that we did in this space was published in Nature BME. And in this work, what we were trying to do was to figure out, well, with retinal fundus photos, can we detect interesting stuff using learning? So back to that paradigm where instead of doing explicit feature engineering, we were asking it to essentially learn the features on its own. And we found actually one surprising thing, the reason this work even started was that we were able to predict the sex of the participant. And then in the initial, this was data from UK Biobank. And interestingly, I think the story here was that the researcher working on this had a number of positive and negative control tasks that they were trying to predict. And one of the control tasks that they had was supposed to be a negative control, and this was to predict sex of the individual, of the patient. And that, for some reason, was lining up with a greater than 0.9 AUC. And we just couldn't figure out why it was that was happening. And after a lot of investigation, we ruled out a lot of causes, and it turns out that sex was something that could be predicted alongside age to about 3 mean average ever, and a number of other factors. Similar things happen when we looked at trying to predict blood parameters like hemoglobin and detection of anemia, as well as a notion of a aging, kind of like a biological age. So we did a bunch of work in this novel signals kind of space. So that's all in kind of like using fundus photos. And another thing we then did was, and this is another surprising thing, was we worked with a partner for whom they were, in addition to the fundus photos, they were taking photos of the outside of the eye. And what's interesting there was that they were taking those photos mostly to see if the person might have a cataract if the eye positioning was right, if there's any other issues that might explain findings on the inside of the eye, the retina. And when we plugged those photos into deep learning, we found that it was able to predict many kinds of diseases, ranging from diabetes to liver function to kidney function and more. And we validated that across a number of different sites across the US. And also we extended it to different kinds of biomarkers in the second study. Now, this was a bit of a surprising finding. And so what we then did was that we applied image generative techniques in this particular paper to try and understand if how the model was able to do this. This is something so surprising. And some interesting things kind of like popped up here. Now, first of all, for some of the findings that we had, these were positive control findings. And so the way we approached it was that we had asked the model to predict if it was the presence of cataract on the external eye images. And the cataract should be a opacity or kind of like a cloudiness in the eye, so you should be able to observe it. And using the generative techniques, we did see indeed that the model was able to learn kind of like image transitions that look like the pupil getting more cloudy, the lens getting more cloudy. And so that was a nice positive control. And based on that, we also found that for certain findings like A1C, there were certain findings around the eye that seemed to be correlated with that. And we had some hypotheses about how that might be the case. We also found interesting things around bias. So one example was when we were trying to ask the model to predict the presence of low hemoglobin. Now, on average, women have lower hemoglobin than men do. And so given that particular problem flaming, the model actually said that eye makeup was associated with that particular prediction task. And this was one case where the model was picking up something completely unexpected. And of course, in this case, it actually was because of the way the problem was being framed to the model. And likely that would be fixed if the model was asked to predict low hemoglobin specific to each sex, and so that gender or sex bias was no longer there. All right, so these are all work that we were doing purely in image space, and we've done the same for mammography and a few other things, and I'll come back to that later on in this talk. All right, so that was all in the kind of like the imaging era, and then after that, of course, language models and chatbots then became very, very popular, and I assume most of the, if not all of the audience members had used some kind of chatbot before. And I think in a nutshell, one way to think about kind of like that transition was that instead of looking at complex inputs going into a model and predicting structured outputs, such as a categorization of a disease, you were now doing things where the model outputs were complex data as well. So that includes text, images, audio, video, and so forth. And a lot of the work, not all of them, but a lot of the work were actually based on autoregressive generations, where the model essentially has inputs and outputs, and in each turn, it is generating one additional output, and that output is going back into the model as input to inform the next generation. This is very simplified. Of course, there's a lot of tricks that makes this a lot faster, and there's a lot of sampling and other nuances to this process that make the quality a lot better. But this does form the basis for a lot of the text-based language model work that we've done. And so that leads me kind of like to this kind of like Gen AI part of the talk, where I'll cover three large categories of work we've done in this space. First, towards clinical applications. Second, exploring the capabilities of the latest models in this space, and you'll see how the models have improved over time as I talk through this. And third, work we've done where the goal is to release models that enable the community to build more applications for their own purposes. So in this first category, I'll talk through the AMY side of the work. This was not actually the start of this line of work. It was predated by the MedPalm series, but let me focus in this section about the AMY work. So one of the projects we did in this space was one where the model has input what's called kind of like case presentations in medicine. And so what does that mean? Well, in a case presentation, the model is seeing things like the patient is a certain age, a certain sex, and a certain kind of like patient history, chief complaint, and other information. And these cases were sourced from the New England Journal of Medicine clinical pathologic cases. And there were a few hundred of these. And now, because these are sort of like pre-created cases and they're very challenging, the model does not need to worry about getting that history from a patient. The model just gets all of that context right up front. In this case, we were doing this with a text-only model, so there's no multimodal component to this particular work. And this was one of the prompts that the model had, where it was asked to be a helpful medical assistant that has information about a complicated disease, and it's supposed to reason through what the possibilities about the diagnosis might be. So given this, what we then did was to run a randomized study, and the randomized study happens in two arms. It's in two arms, and each arm has two phases. The first phase was a clinician that is unassisted by anything. They're asked to just look at the case and present their own diagnoses for that case. And that happens in both arms. In the second phase, for the first arm, the clinician is assisted by search. And what that means is that they're given the option to search online for any materials that they think might be relevant for this. And so that's the first arm. The second arm is when the clinician is assisted by this Amy bot with this particular prompt. And so they can then interact with that Amy chatbot and ask more questions and so forth. And in addition, of course, we tested Amy bot just on its own without any human intervention. In this plot, what we see is the differential diagnosis accuracy versus the ground truth from the New England Journal of Medicine. And then top N refers to the position in a differential diagnosis. And just for context, a differential diagnosis is essentially a ranked list of possible diagnoses for a particular case. So to the right, what you'll usually see is the lines will trend up because as you're given more chances to guess at a diagnosis, you usually get more diagnoses correct. Now, what's interesting here is that if you look at the phase one of both arms, that's when the clinicians are unassisted. They're asked to guess diagnoses before they consult any reference materials for these complex cases. They actually had pretty relatively modest performance over here, starting at under 20% and going up to slightly above 30%. So that's the blue line over here. When they now had access to using web search, they now jumped up by about 10% throughout the board for all positions in the diagnoses. And then when we look at now clinicians were assisted using AI, the first couple of positions don't change very much, that's the orange line, but the later positions get an additional 10% boost. So that's kind of like the results for the orange versus green that reflects the randomization part of the study and the gap that we see between clinicians. Now, what's a little bit interesting is that in addition, if we look at the red line over here, which is the performance of the AI in isolation, it actually got better performance, particularly towards the end. That's where you see the confidence intervals are no longer overlapping over here. And part of this gain that's more sort of kind of like later weighted is the fact that the AI is able to provide more guesses even when it's the 6th to the 10th position, versus on average, the clinicians were not usually providing that long of a differential. So part of the benefit towards the end is that, but even towards the start, you do see that there's still a 5-ish% gap between the AI assisted clinicians and the AI in isolation. So as a reminder, these were on challenging cases from the New England Journal of Medicine, but the AI did not have to figure out anything about history taking. So then the next thing that we did in this general space was that we did something similar with the AI, but then we were tuning it to be conversational and to solicit the medical history from a person. And the way we tested this was in an OSCE style study. OSCE stands for Objective Structured Clinical Exam. And this is a form of assessment that's used with physician trainees, where they're training to understand how to take a history of a patient and to make sure that they're asking all of the right questions. And the way we ran this study was that there was a library of scenario packs that we had a professional kind of like OSCE lab help us with. And then patient actors, so professional people who are trained to act as patients, were given the scenario packs. They do not show the AI the scenario pack, but then these patient actors interacted with either an AI or a PCP. So those are the two arms in this study. And then what we test are whether the AI or the PCP get the diagnosis right in a very similar format as you saw on the previous slide. And so here again, we see something kind of similar. A PCP, a primary care provider, at a pretty reasonable kind of like accuracy that goes up as you get to higher diagnosis positions, but the AI in this case was still higher. One thing you'll note here is that the y-axis here is a little bit higher than the previous slide, and part of that is because in the previous slide, these were much more challenging cases published in a journal, versus here, these are slightly more typical cases, even though we've made an effort to diversify them. A few caveats here. One, even though the AI is doing this medical history taking, it is still with patient actors, so these are not real patients. And second, this is all done using a chat-based interface because that's what's available when you're talking about working on these AI-based chatbots these days. And so this doesn't reflect clinical like diagnostic process where a physician might be talking to a patient either in person or via a web interface. We did, in addition to kind of like the diagnostic accuracy assessments, there's more work in the paper showing different axes that we evaluated things against, and that includes empathy and communication, where the AI, because it's a lot more, I think verbose is a good word for this, but a lot more careful in its framing, had much higher sort of like empathy related scores. And so overall, I think what we found in this study was that AI was better at a diagnostic history taking, as well as providing empathy and communicating with the patient. And in the next sort of like slide here, this talks a little bit about work where we extended what you saw in the previous slide, the previous couple of slides, into arenas where these are subspecialties, including cardiology and oncology, and these were collaborations with different institutions. And then we tested Amy on these cases. And a lot of things we focused on here was that given these much harder subspecialty related cases, was the model's outputs a lot better? And one thing you'll see here, you look at the preference data over here for Amy in red versus a comparator clinician in blue, was that the comparison here is a lot less kind of like one-sided, like what you saw in the previous couple of slides. In fact, there's some amount of neutral scores, which are the ties in the middle over here. Another way of looking at this plot, though, however, is to look at this as how many percent of the cases is the model at least as good as the comparator arm. And so to look at that, you're looking at the solid color here alongside the tie. And so here you're looking at something in the range of 60 to 70 or so, which is not bad, but definitely not perfect. And a very similar set of results are seen for the oncology related work. All right, following up on that, we then started thinking about how do you improve this further? And a couple of work in this space, number one, was to then extend things such that the AI is able to do reasoning over guidelines. And so in this plot over here, what's happening is that there is a patient or patient actor interface where they're conversing with the AI. And there's an agent that's pretty fast that handles the actual dialogue. And there's an internal state for that dialogue. And that internal state then informs a retrieval step by a model that looks up guidelines that are relevant. In this case, we use guidelines from the BMJ and these families. And then the model is using those guidelines, grounding on that, and providing management kind of like drafts. And so this overall kind of like agent-based framework, what's powering what we're doing with this kind of like guideline grounded diagnostic reasoning. Another thing we did in a separate work was to try and figure out if in addition to this text-based chat interface, if these multimodal models can then handle multimodal inputs. And in this case, we thought that the most reasonable multimodal inputs that you expect the average patient to have access to are things like scan images and reports and other things that some consumer electronics may be able to provide you, such as EKGs. And here we had a similar kind of like form where the Amy bot was having a dialogue and there's an internal kind of like state that is being kept. And in this case, the state, what was happening was that it was going from a history taking state to a management state to answering follow-up questions about the state. In this particular case, you'll see that the arrows here are unidirectional. So it's flowing from one state to the other. But of course, kind of like in a more idealized world, there can be also state transitions back, although that will incur a little bit more complexity. Now, this is very recent work released very recently. And in this work, what we were doing was to try and reimagine how one would use these things in practice. And what I mean by that is that to have a fully autonomous AI execute on diagnostic reasoning is a really good research project. It may be a little bit hard to do that in a real world if we need to have some level of oversight and we want a safety component to be handled completely. And so here, the concept we're introducing here is an asynchronous oversight paradigm. And we introduced this kind of like term guardrail, standing for G. And so G, I mean, what it's doing is that it's trying to do just the parts that are unlikely to have any safety aspects, safety implications. And so what's happening is that the patient is interacting with an AI, and then the AI is taking the history of the person, and then it's reasoning about what the possibilities are, but it is guided and tuned and guardrailed not to provide medical advice directly to the patient. Instead, what it does is that it drafts a note that includes both the subjective and objective, which means subjective are things that the patient's reporting they experience. Objective are what the patient, what data you can collect using other means. They are objective, so not self-report. And then assessment and plan are from diagnostic reasoning. So what do they think it is? And the plan is what should happen next. The AI is also presenting a kind of like a draft of a message for the patient in terms of next steps, or something that says, hey, here's a follow-up and we need to chat more. And so what's happening in this guardrails for the AI situation is that that's a guardrail AI, and that's going towards a overseeing physician, kind of like supervisor, that's checking these information before it goes back to the patient. Now, of course, this is a study setting, so this is not a real case, but this is a paradigm that we think may be a possibility for being able to incorporate some of these things into a clinic. Now, in the study setting, what's also happening is that the comparator arms are so-called guardrailed PCPs and guardrailed physician assistants or nurse practitioners. And these guardrailed kind of like human arms, what's interesting is that these are a departure from what these individuals will be doing in the clinic. So we saw some slightly counterintuitive results they can read more about in the paper when it comes to these. But by and large, what we're finding was that the guardrailed AIME agent was doing a really good job of avoiding medical advice while collecting the right data and providing drafts that needed fairly minimal editing from the overseeing supervisor. All right, so in the interest of time, I'll skip more of the details here. And then not building directly on the last slide, just due to chronological order, but we're now executing on a study with a fully IRB approved protocol and with consented patient at the Beth Israel Deaconess Medical Center. All right, so that's a overview of the AIME arc of work. I'm going to now switch over to talking about some of our work we've been doing over time in exploring the capabilities of these latest language models. And this jumps a little bit back in time. And so here's a chronological part of this time series, where if we look at this, this is back in 2022 or so. And so in this work, what we were doing was building on what was then kind of like a contemporary model, PALM-1. And so we built upon PALM-1 to understand if the PALM model could answer USMLE style questions really well. And these were questions from NetQA. And so before that, there was some progress starting from 30% range to 60, and there was quite a bit of a jump when we applied PALM-1 to this. Now, in this case, the way that the PALM model was tuned was using a soft prompt, which is rarely done these days, but in those days, the soft prompt was something where instead of having a token that represents actual text or hard tokens, there's a soft token that's provided to the model that tunes its behavior to be better for a certain task. Now, after that, we then tackled PALM-2, which was a more recent model at the time. And in PALM-2, we showed there was a further and actually even a bigger jump than the previous PALM-1 jump. And so PALM-2 was one that actually had pretty reasonable performance and beating the kind of like the expert bar for this task. Now, after that, what we then did was to apply what was called PALM-E. PALM-E was actually based on PALM-1, but what it had was the capability to incorporate encoders for other modalities. And what we did in PALM-M series work was to have a single unified weight model that's able to handle a number of different modalities, ranging from genomics to dermatology to pathology. And what we showed in that work was that it was able to perform pretty reasonably well on a number of different tasks spanning all of these different modalities, not exactly still for every single task, but approaching that for many tasks. And what was interesting here is that this model at its time, this was using a single unified set of weights. And so the part that's interesting here is instead of thinking about tuning things for every specific modality, somehow this model was able to work across all modalities. And today we might take that for granted. At that time, this was quite a bit of a change versus what others were doing. Another project we had in space was to try and understand the health equity point of view. And so we released in Nature Medicine this paper, and this was what we call a toolkit. But essentially what we're trying to do was across a bunch of different data sets developed by a number of different people and communities, we were trying to understand if there were bias in these model answers. And one thing that we learned here that I think was a little bit underappreciated in the literature at that time was that who does the ratings for these bias, and fairness related ratings was very, very important. And what that means is that the lived experiences of the rater and their expertise affects how they see things as being biased versus not. And so, one of the main learnings here really is that, as you look at these papers and you understand and people are reporting bias numbers, you have to look at who's doing the ratings because that can really affect the results. And we found that kind of like similar to how doctors can disagree and there's high inter-rater variability. In this case, we found that between the different kinds of raters, there was extremely high inter-rater variability. And sometimes even within the same category of raters, for example, laypersons, based on age and other factors and other lived experiences, they were also rating for bias in very different ways. Now, some of this potentially could be handled based on guideline improvements and instructional improvements. But what still remains, though, is that the bias they were flagging were things where they perceived things as being biased. And that really depends on, what they feel. And so it's a somewhat subjective assessment. All right, so that work in the previous slide were based on PALM-1 and 2, and then later on, as the Gemini initial series of models, the first Gemini models arrived, we started working with Gemini and to investigate the potential in this space as well. And so there were two kind of like papers in this space that we released. One was looking at its text-based capabilities as well as its ability to use tools such as web search, as well as to understand videos. And so that was one of these papers. And the second was one that focused a lot on the medical-based modalities, spanning imaging to genomics and other things. So this, in some ways, was a spiritual successor to the MAP-M related work. Now I'm going to shift gears very slightly away from the very clinical pieces of this to thinking about what's very relevant to consumers. And so for consumers, sometimes they are getting data that's medical-like, not from the physician, but from their wearables. And so wearables will include things like smartwatches and fitness trackers. And in this case, what we were trying to do was if you had data from the wearable, that's additional context about the individual. Can you use that context to inform questions that they might have? For example, did I sleep well last night? And how can I improve my sleep and so forth? And so that was work that we did back in 2024. It was published recently in Nature Medicine. It focused a lot on coaching for things like activity and for sleep. And there was a number of different kinds of evaluations that we did here that spans things like standardized exams all the way to specific case studies that were written by experts in that particular space. Now, at the same time that that work was happening, we were also doing work using what we call the insights agent, where the goal here was use at the time the React framework to create code that can retrieve information that is relevant to what the person wants to know. So in this case, for example, if the person is asking about their sleep, this framework is then generating code that retrieves from the right data frame to figure out which data frame they need, and to write code and then extracts the right information that's relevant for that particular user query. And what's interesting about this framework is that because there's a loop over here, that reasoning enables that framework to understand if there is, let's say, a error message from that code, and then to essentially recover from that particular failure. This was working pretty well in terms of kind of like a data science driven answers to user queries for personal health purposes. Now, very recently, just a couple of weeks ago, we released what we call a personal health agent kind of like framework, which starts to bring together a lot of these ingredients together into one overall unified system. And so one big part of the work was really trying to understand what do users want to do with this. So a lot of this relates to kind of like core needs from wearable users, such as sleep and activity. But here it started doing kind of like much broader understanding of users from common health queries and others. So we then found sort of like four broad categories of CUJs. CUJs, for those who are not in that particular space, stands for critical user journeys. These are ways to describe what are common usage patterns for products primarily that people have needs for. And these four CUJs, it turns out, maps to three high-level kind of like agents that one can create. And so, for example, if people have general health questions as well as like general wellness, general sort of like symptom-related questions, that can map to what we call a domain expert agent, which is really thinking about expert medical information. If people have questions around their personal data, this is where the data science agent, and it's built off this earlier work about the insights and code generation. And if people have kind of like general wellness and coaching needs, then the health coach agent was built to satisfy that need while really using these sort of like well-grounded coaching-based principles to help guide people's behaviors. So this is all work that we're doing specifically to help people derive more value from the wearable data and to live healthier lives. Now, another thing that's in wearables is the actual underlying data. And so another work, kind of like line of work, what we call the large sensor model, was trying to figure out, can we get these kind of like as raw of a data as we can get from these wearables? And can we model them and extract interesting value out of them? And in some ways, these are all time series of different forms. And how can we work with these kinds of time series? And so this was kind of like going back slightly more towards foundational modeling and looking at the scaling laws and how compute data size, model size, and other things are varying the model error or losses. And we saw kind of like very similar plots with a little bit of plateauing towards the end. In the initial work, what we initially did, and all of the data here were presented in form of per minute data because the raw data traces are usually not stored. And so per minute data then stretched out over hours or days in one axis, and the different kinds of data, sort of like sources. So for example, conductance, heart rate, and other things along kind of like each row over here. And because people actually they can't kind of like wear these 24/7, they need to at least take it out for charging. Sometimes they forget to kind of like, wear it again. There's some amount of missing data. In this case, in this initial work, what was done was imputation to handle the missing data. In follow-up work, what was done was then to treat the missing data as its own modeling problem and providing masked tokens over here, and then treating it as part of the modeling problem. And then we saw further gains in performance by doing that. So that was the second paper over here. Now, another line of work then asked the question, well, when we look at these kind of like tracings from wearable data, it's actually the case that you can extract additional value out of these. So these include things like statistics, And it includes things like free language summaries of what's happening. For example, broadly speaking, this person is getting higher and higher resting heart rate over time, or broadly speaking, they're getting more steps over time, or getting better sleep, and so forth. And all of that language was interesting because there is semantic meaning associated with that language. And so in this work, which we call Sensor RM, what was happening was to apply a contrastive captioning kind of like approach to that. And so modeling both kind of like the input essentially as an image, and then the output using this free language. And then we showed by doing that, some interesting capabilities started emerging from this, kind of similar to what we observed when we're looking at image captioning. Right, so that's the kind of like a second category of work in the wearable space. I'm going to switch gears again to talk about what we then did with a lot of these kinds of work as we did the modeling internally, and then we wanted to increase the scale of kind of like impact that we could have by enabling the community. And so in a nutshell, what we did was we started to, as Simon said earlier, release these open models. And the open models cover a variety of different kinds of input modalities, ranging from kind of like image-like or time series-like to kind of like molecular representations, other things that you don't classically think about as actually text. We're going to talk a little bit more about these different ones in the next few slides. So one thing that we released here are just foundation models or encoders that are based specifically for each modality. And in the imaging space, we actually had done a lot of work for specific tasks. One of the examples that I talked about earlier was for diabetic eye disease, but we've done this for a number of different other tasks as well. And so for each of these categories, what we were then doing was we were trying to understand for the tasks that we had approached before, for example, chest X-ray findings, Gleason grading, this is for prostate cancer, using pathology images, identifying skin images and skin conditions in skin images. And in this case, these were acoustic signals. So this was for understanding whether audio segment contains signs of disease. And for each of these tasks, what we then did in this work was understand if we improve the encoder that we start with. So instead of starting from ImageNet, if we improve the encoder using some kind of self-supervised learning, and for these different problems, we use different kinds of SSL techniques. What happens if we start from those and then titrate the amount of data that the model that we use to train the final classifier? And by and large, we saw that we were able to reduce the data needs across all of these tasks by starting with a better encoder. And so what we did with these models was to start to release them as APIs so people could build upon these foundation models for their own purposes. And we started to get pretty good feedback from the community, their experiences using these foundation models. As I mentioned earlier, some of that we done, we started to work on molecular predictions. And the way we did that was to actually use a representation of the molecules that looked very text-like. So specifically, these were smiles-based representations. We can see a couple of examples here. And you can use these smiles representations as input to the model and ask it to predict certain things. In this case, these are numerical predictions, but it could do classifications and other things as well. And so this was work that was originally called the TXLM series of work. And then later on, as it got extended and built upon Gemma 2, it was released as TX Gemma. And Gemma 2, TX Gemma is now available for use. And another kind of work that we've done in this space was to then start to combine all of the different modalities work and to look at both the image encoder and language decoders. So one thing we did here was, if we look at the right side over here, there are imaging modalities that we used. And we used that to train a encoder. In this case, this was a transformer-based encoder and trained using the SIGLIB loss function. And this was a 400 million parameter image encoder. This encoder was then used for the language decoder in MetGemma. And so that 4 billion multimodal model was released first, followed by a 27 billion multimodal model. This text-only 27 billion sized model was released more sort of like earlier in time to the multimodal 4B, mostly because at the time this data was sort of like ready for use a little bit earlier. But then later on, we added on the FHIR or medical records related capabilities as well as the multimodal capabilities. Both of these models are now available in the HiDef family for use. Here's one of the plots from the paper. And here what we were seeing was we were trying to compare what is the pricing for using the model. And this is kind of a proxy for understanding model size and compute requirements. And looking in this case, just as a proxy of performance, the MetQA score. The tech report that we have has a lot more details and a lot other evaluations. So here's one example of the evaluation we saw in MetQA, where if you compare Gemma 3 with the medically tuned version of it, there was quite a bit of a jump even for the base Gemma model, the 4B size, and without further fine-tuning. Gemma 3 is over here. It's a bigger model, and so by default, it performed quite a bit better than the 4P model. And then if we look at MedGemma, the same size model, it goes to the right a little bit because of thinking, but then the performance is substantially higher, and you can see it actually approaches the 0.9 bar, which was what we were seeing in some earlier MedQA benchmarks for much bigger models. This is a demo. I'll try to see if I can play it here. But in this demo, what we showed was using MedGemma to interpret images as sort of like in this particular concept, and then to explain each of the findings and impression elements that exist in this particular synthetic report that was generated. This was a little bit of a localization capability sort of like demonstrated here, but as you can see, the granularity of this isn't very high. In this particular demo, we have both X-rays, CTs, and others as well. Here's the second one. This one I'm not going to play, but what's happening in this particular demo was that we showed what would happen if you select different scenarios. And MedGemma is used as a kind of like an AI agent that a simulated patient can talk to. And you see on the left side, this is the transcript. In the demo, if you try out the URL below, the audio is actually being played using the text-to-speech engine. And in the Generative report, what's happening, this is being updated over time. As the conversation proceeds, the kind of like the information here is being updated based on what the simulated patient here has said and what the AI has captured and asked for clarifications on. So this is kind of like a mock of a AI agent that can help with a clinical intake part of the workflow. If you look up MedGemma on Hugging Face as an example, there's been hundreds of thousands of downloads over here over time. And so if you're interested, please give it a whirl, and please give us feedback at our developers forum as well. All right, switching gears a little bit, this is an effort not by us, but it's by James's lab over at Stanford. And so what they have is this thing called MedArena, which is kind of similar in spirit to the LIMSys or Chatbot Arena. And so here what's happening is that people in this case, these are all doctors who log in using a physician ID. They can try out models in a blinded way. So they have a left side and a right side model. They provide the same query. They can continue to submit queries to both models. And they don't know which model is what, but they're able to vote on which model, left or right side, is better versus worse. And so over the course of many of these kind of like what they call battles, to chess scores out of it. And if you rank it by doing pretty well near the top of the leaderboard. So if there are physicians listening, please feel free to try out. It's a great way to understand the performance of these models in kind of like a blinded way without necessarily knowing what model you're interfacing with. So this is the end of my presentation. To conclude, we've seen quite a bit of work where AI can help scale care. An example end-to-end that I talked about was diabetic eye disease, but we've seen examples from ourselves and from others in other domains as well, spanning mammography, endoscopy, and others. AI can also help discover novel signals and find things that people didn't know to look for. But as you launch these things, it's really important to continue to monitor these models to see what the performance looks like, because you might find that it's performing better or worse, and depending on what's happening, you might be able to trace back what the issue might be. Sometimes we found there may be aspects such as different devices that got deployed, or even something as simple as a dirty lens that might need to be fixed. So being able to monitor device performance is really, really key. Now, in the generative AI space, the capabilities are advancing very rapidly. And so we have to keep that in mind as we look through the work, even work as recent as 2 years ago, where the methodology is quite different than maybe what you would use today. But what these models and capabilities are powering are applications ranging from conversational agents to multimodal analysis to working with molecular kind of like inputs and making predictions that are relevant for therapeutics, to incorporating wearable data that consumers may have access to personalize the insights to help them live healthier lives. And we're releasing some of the open models that's based on work that we've done over the years for people to build upon for their specific applications in their jurisdiction, and to really take kind of like ownership and build upon and sort of like kind of like power what they are most interested in. If you're interested in testing some of these like non-medical models, you can head over to MedArena.ai for free. And with that, I conclude my talk. Thank you so much for your attention.
Great. Thanks, Yun, for the wonderful talk. You cover a lot of interesting work at Google. And so there are, for audience, if you have a question, please either just ask directly or put in the chat. I think we have one question there by Yupeng Li. And yeah, in the pharma industry, we only have fixed data set cannot ask a patient to provide additional data or symptom. In most of the cases, don't have the complete history of the clinical events. Can we still leverage a large language model like AMI to predict patient diagnosis or treatment?
Yeah, that's a good question. So I think, if you're in pharma, I would kind of assume it's generally speaking working on retrospective data. This is a pretty common, I think, sort of like situation, because some of the retrospective data honestly is being sourced from the same few players and underlying institutions. But essentially, kind of, I think the question is really about what can you do with retrospective data and is that useful? Um, it's a good question. I think it depends on what your final application is. So, for example, there's a lot of work, there was recent work from Microsoft, for example, looking at modeling EHRs and using that to perform a variety of different tasks. I think they had more than 50 tasks in what they were doing. And so for that, I think the static existing retrospective structured information is exactly what you need. If you want to use the retrospective data to essentially simulate what would happen if you were to kind of like have an AI intake agent, for example, then for that, you need to figure out if the retrospective data contains the information you need. So for example, sometimes if they contain something like a SOAP note, the history part of the SOAP note might actually give you a pretty good amount of information on data, symptoms, and other things. There are going to be things that are very hard to know about because it's just not in the note because the physician didn't ask about it. But occasionally, you might be able to tease it back out from the longitudinal record by looking at either earlier records or later records to then tease out some of this contextual information. So depending on your task, this might still be quite doable. But I think you have to figure out how do you frame it in terms of the final application that you have in mind. Hopefully that addresses.
Yeah,
And
thanks.
then
Yupeng, you have some follow-up comment you want to?
Yes, I have another follow-up. Like a lot of data we have is claim-based, so there are no like natural language claim like the clinical notes. So do you have any suggestions how to deal with the claim data?
yeah, it's a good question. So I think claims data is used for a few applications very commonly. One application is used is if you're linking up with EHRs, people use claim data to do kind of like billing code related predictions because it's a sort of like a big industry. It's important for billing. Another thing that's being done, I think, if you want to predict outcomes from billing data, you need to figure out ways to get the data into a form you trust. And what I mean by that is there's simple things you can do, such as just doing a filter on the billing codes to say, hey, you need a few, X number of billing codes of this particular code before you consider it as a hard outcome that's occurred. So you need to find kind of like what kind of outcomes you're interested in. Um, for natural language specifically in that space, I think folks have done some interesting work in the sense that billing codes are both codes. So there's the numerical code, depending on what coding system you're using, the alphanumeric code. But in addition to that, most of these billing codes have free text associated with each code. So in principle, you can leverage that free text associated with the alphanumeric code to do some interesting NLP-based analysis as well. But generally speaking, if you're thinking about doing predictions, there is probably a lot of value in figuring out a way to link it up with EHR and other data because it's just much more granular.
Yeah, thanks. One thing we are trying to do is just use the description of the code as a natural language. But one challenge we are facing is like there are like thousands of codes. So if you turn into like description, there will be like millions of like tokens. So it's difficult to like distinguish which one is really important.
Yeah.
But uh, yeah, but thanks for your insights.
Thanks,
Thanks for the question.
Yupeng, for the question. Hanyin, you have a question you want to ask?
Yeah, thank you, Professor. And thanks for the great work. And I learned a lot. And I've read through all the series papers about AV. And I do have a quick follow-up question about some of the details. And by the way, I'm a CS PhD student with Professor and also internal medicine physician at Mayo Clinic. I'm wondering for the AMI, I'm in terms thinking about what is required for LLM to tackle a task like AMI, just because of the nature of the challenging clinical knowledge, especially long tail knowledge. I can specifically think of at least two requirements. One is the understanding of the knowledge, especially the long tail knowledge, and the second is the reasoning. I'm wondering from your experience which part is more important, and probably if you feel the reasoning capacity in that regard is different, the general reasoning, for example, when it comes related to the mass test. Just curious on your take.
I think you or
Sorry, I think I froze. The last part I heard was if I think the reasoning capacity is something, and then I think that's where it
Oh,
cut off.
I'm just wondering if you think that clinical reasoning is the same type of reasoning when it comes to the compared to the mathematic test or the coding test. Yeah.
Yeah, okay. So I'll sum up the question as kind of like, there's I think a knowledge problem and a reasoning problem in this, and then kind of like which part's more important. Um, I think some of this is philosophy, honestly. And I think in some ways, if you think about a very capable model, what you might call knowledge for a very capable model might be called reasoning if the model were smaller. And so, mathematically, you would think about maybe there are axioms that you kind of like build up from. And then those are the things that you think about as kind of like the knowledge base. And then the reasoning what that gives you is it lets you build up to more things beyond that. So I think in medicine, there's maybe a parallel that you can think about that's kind of like similar. And so maybe one thing one way to rationalize it is that there's I mean, it's imperfect, but there's kind of like the basic anatomy and physiology that medical students are taking the first couple of years of medical school, and that influences how they think, and pharmacology, other things, but that influences how they think about, what's happening in the body and learn about these disease systems. Now, once you get to kind of like management plans for people, if you think about just single diseases, a lot of that insight kind of like sort of translates mostly directly to understanding, okay, I'm gonna treat and manage in this way because of this. So that's part of this reasoning paradigm. Now, when it gets more complicated and more nuanced, either with comorbidities and multiple diseases, or if there's treatments and therapies where you don't fully understand the mechanism, I think that starts breaking down a little bit. But I think high level, I think it's a bit of a mix of both. But depending on the size and the capabilities of the models that you are working with, that mixture may be a little bit different just because of what the model is capable of. There can be things that look like a complex task to a small model where they reason for many, many tokens. And then for a much larger model, it just goes, boop, that's the answer. Like this is straightforward because it's to that capacity and that capability sized model. It's an easier task.
Thanks, Yun. I know we're on top of the hour. Yun, do you have a few more minutes to answer your
Yeah,
question? Or-
I have a few more minutes.
Okay, great. So feel free to add more questions, but I have a couple of questions. One is on this. On one page you showed a whole bunch of resources, open foundation model that Google has released. I noticed that there are imagings, there are other modalities, but there's no like EHR type of foundation model. Like that seems in my mind is a big, very common type of medical data that people may want to use some kind of foundation model to support various tasks, even including I think this claims data. I put that into this roughly still the same type of EHR type of structure, longitudinal data. Do you have some comments on why? I mean, I don't understand why hasn't Google released such a model, but is that like a?
Yeah, yeah.
You think there's no such need, right? Because of the, or there's some gap in terms of the training data that make this as impossible, or and can you make some comments on that?
Yeah. I think so I guess the direct answer is I guess the multimodal 27B MedGemma model does support fire records to some extent. That is supported. I would say that its capabilities in sort of like understanding full-on fire bundles and more complicated structures there are probably not as mature as we would like. It's something we're interested in improving over time. And we do have kind of like plans to continue to improve that, broadly speaking, the entire family of things that we are releasing. So I would say look out for more for more to come there. So hopefully they'll be better. Kind of like I think high level, kind of like part of the reasoning there is just building upon the past work that we've done. It does mean that we focus on specific areas where the data sets and experience and the learnings are already available, and those are the ones we kind of like prioritize building towards first, which is part of why that sequencing happening that way. But we're definitely interested in making kind of like fire records and EHR work better. Billing codes, I think, are a little bit more of a different story. I think because there's billing codes and there's kind of like specific coding systems, ATC for medications, and a whole bunch of other things, each of which have their own quirks some of the coding systems even have this kind of like complexity where it needs licensing to go work with. And so I think there's some additional complexity that will need to be worked through to work with some of these.
That makes sense. Yeah, I would love to use this EHR foundation model if that Google research released that. And the other thing so you mentioned, you really talked about this really paradigm shift, right, from the classical machine learning to deep learning model to foundation model to this agent. And so looking at this trajectory, what do you see as the next paradigm, I mean, in this kind of direction?
That's a good question. I think it depends on what you're interested in. I think there's always progress to be made across many areas. I think from my personal interest perspective, I'm thinking about, kind of like real applications for people. And for that, we need kind of like robust models. We need models that are well, that's both able to reason and that we can trust the reasoning and that the reasoning actually supports what it's outputting. And we want these capabilities to be kind of like reliably good. And so not just in terms of kind of like static benchmarks and such, but reliably good in the setting of the real world. Because the real world is very, very messy. And so anytime you interface with building something and there's real users using it, you realize they may be using it in ways that you're not expecting. And you need to be able to handle that elegantly. I would say that for some of the earlier work we did in the imaging space, we did try to handle those things by kind of like in a, by today's standards, primitive way, detecting when a model might have as input, this is in the eye imaging space, so it might have input a non-eye image, and then say that this is not an eye image. And so there's some sort of like primitive kind of like error and quality checking and stuff like that. So I think the high level equivalent spiritual successor to that may be necessary in this space going forward as well.
That's definitely very true. Maybe last question. I always ask our speaker to give some advice for our students, especially if you thinking backward, maybe 10 years back or maybe longer at MIT, or a lot of grad students today, right? So struggling from what topics to focus on. I mean, this AI evolving so quickly, they don't have enough compute or data set, or just a lot of excitement, but also constraint, right? What advice do you have for all the grad students today?
Yeah, that's a good question. I don't know if I'm qualified to give advice because in this particular environment, because it's so dynamic and fast changing, that I feel like any sentiments I have today may be outdated quickly. I'll give it a shot at sort of like what I think are sort of like high level principles that I feel like what will be useful. And I think one thing is to figure out, what drives you in your life and your career, and seek out ways to keep yourself working on something that you're very motivated by. So that's it, I think, in terms of like overall satisfaction. Um, However, if you also have additional, I guess, goals. So, for example, some people may tell me, I want the job industry or a specific team or company or whatever. And some are like, I want to create a startup and create a next big thing that really changes everything. I want like a revolutionary change, not evolutionary change. Then figure out kind of like those possible pathways and talk to people about how what their perspectives are on those pathways. Try to get as much experience as you can with those pathways. And what I mean by that is that sometimes the pathways that you think is something that you would love may not be what you expect from it if you think about the day-to-day life. So try out. I think it's the best way to understand it. Talk to people, figure out what drives you, what motivates you, and find something that you love doing, and ideally you can get paid doing it, but find something you love doing.
Great. Thank you. With that, I really appreciate Dr. Liu's insight and the wonderful talk. Thank you for sharing all those. Thank you, everyone.